Okay, so thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Armando Angrisani to give us a talk on simulating quantum circuits with arbitrary local noise under Pauli propagation. So Armando received his PhD in computer science from Sorbonne University in Paris, France in 2023. He's currently a postdoc in Zoe Holmes Group in EPFL in Switzerland. And his main interest is in the interplay between quantum information, quantum learning theory, and classical algorithms for simulating quantum systems. So Armando, the floor is yours.
Yeah. So thank you for inviting me. So I'm going to talk about this recent work we posted on the archive at the beginning of the year. So it's part of a longer series of work on Pauli propagation that we are studying in different settings, both with noise, without noise, on scrambling circuits or on near Clifford circuits and so on. So this was a joint collaboration with Antonio, Manuel, Marco, and Zoe. And so, like before giving the details of this exact project, I have a few slides on Pauli propagation, which are more or less the same also Manuel had, I think, but it will be, I think, a nice reminder. So there are many different names in the literature for very similar simulation framework. So when we talk about Pauli-path simulation, operator backpropagation, and sparse Pauli dynamics, we are more or less referring to the same framework with maybe some really tiny difference. So yeah, like with this simulation approach, we represent the entire computation with a tree-like structure. This tree will grow exponentially fast if you want to compute it exactly. And so what we need to do to make it classically tractable is to introduce some truncation rule, that is, some branches of the tree will get truncated because we don't expect them to contribute significantly to the object we want to compute, which is typically an expectation value. Another very important practical aspect that I will not discuss so much is that it's also very advantageous when we can to merge different branches, because different branches can lead to the same Pauli. And in most theoretical analysis, this merging part is not considered because it's actually, like, at least theoretically, is easier to analyze the path one by one. But in practice, if you want to have something efficient, you also need to merge them properly. So yeah, the object we want to compute, at least in this talk, will be an expectation value of a parameterized circuit u theta for some parameters theta. And typically, we can imagine this circuit as something made by Clifford CI and some Pauli rotations with some angle theta I. Now we will work in the Pauli basis, and this means that applying the Clifford operation is really cheap because they map a Pauli to another Pauli up to a phase. And on the other hand, when we apply some Pauli rotation, we can either get the same Pauli back if the generator of the rotation and the Pauli we are evolving commute, or otherwise the Pauli will split in two. And so by applying this process in an iterative way, we can build this Pauli tree. Yeah, then like at the practical level, there are also many different ways in which one can explore the tree. We can do a breadth first search or a depth first search, and both have different practical advantages. But like in this work, we also consider a further operation, which is noise. And so we model dissipation as some single qubit channel, which is applied on each qubit after every layer. So this is sometimes called the uniform noise model in the literature, as opposed to the gate-based model in which the noise is only applied after the gate. So in general, we can represent a single qubit channel as its action on the four Pauli matrices. And we can also express this more compactly with a matrix, which is called the Pauli transfer matrix. And you can already see that some elements are zero. And this is coming from the trace preservation. That is, when we apply a channel to, for example, Pauli X, we know that we will not get an identity because otherwise the trace will not be preserved. So actually, in practice, we can also work with matrices that are even sparser than that, because we can exploit something which is called the normal form of single qubit channels. So any channel n can be rewritten as in this equation A34 as the composition of a unitary V, a channel n prime, and another unitary U, such that the channel n prime has only 7 non-zero elements. In particular, one element will be 1, and the others are given by the vectors T and D. And here we already can discuss the first distinction between the two main family of channels. So first distinction is between unital and non-unital channel. A channel is unital if it preserves the identity, that is, if it maps the maximally mixed state to itself. And here, in order to get unitality, we need to set these parameters tx, ty, and tz to 0. And otherwise, the channel is said to be non-unital. And like the main scope of this work are non-unital channels. This is because most unital channels were actually already covered by previous simulability results. So we can also make a more fine-grained classification. So among the unital channels, an important family is the depolarizing-like channels, which obviously include the depolarizing channel. And we say that the channel is within this depolarizing class if the parameters dx, dy, and dz are all smaller than 1. And a channel of this form always increases the entropy. And then if you apply the channel multiple times, you will converge to the maximally mixed state, which is the only fixed state of the channel. We can also consider dephasing-like channel that they are still unital, but then one of these three parameters, for example, dz in the typical dephasing channel, is equal to 1. And the other two are equals, and they are also smaller than 1. So now the entropy may stay the same or may decrease or may increase depending on the input state. So for example, if you have a computational basis state and you apply dephasing noise, the state will remain the same, but for any other state, actually the entropy will increase. And now there is not a unique fixed point, but the fixed point is now a diameter of the Bloch sphere. And finally, we can also consider the non-unital the non-unital class. As I said before, the vector t will be non-zero, and now all the three parameters of the vector d will be smaller than 1. And now there is not like a unique interpretation in terms of entropy. The entropy can sometimes decrease and sometimes increase, depending on the input state. And the fixed point is a state which is now not maximally mixed. Now we typically, so the most paradigmatic example of non-unital noise is the amplitude damping channel. So that has the zero state, the computational zero state as a fixed point. And now we also have a more pictorial representation of this. If we have the Brazilian channel and we apply multiple times, we are pushing the state towards the center of the Bloch sphere. For the dephasing class will be a diameter. For the typical the dephasing noise, it will be the diameter connecting the two poles. And for amplitude damping, we will converge towards a fixed point. That could be, in this case, the zero state. Now, another important technical element that I wanted to discuss is that is the adjoint or Heisenberg evolution. When we consider an expectation value where we have an observable, for example, a Pauli, an initial state root 0 and the channel, we can also consider the adjoint map that is now acting on the Pauli and at the end compute the overlap with root 0. And this adjoint map always exists. And it has an important property, that is that the adjoint of a linear map is unital if and only if the original linear map is trace preserving. So this means, so since channels are trace preserving, their adjoint will be unital. And so this means that when we work in the Heisenberg picture, the fixed point is always the identity. The identity is the fixed point both of the unitaries and of the noisy channels. And this, like, beyond all the technical theoretical guarantees that I can discuss in this talk, is already a very important reason to simulate quantum dynamics in the Heisenberg picture when there is a non-unital component. So this is because if we start from the end of the circuit, we know that whenever we get an identity, we can just throw away this identity and forget it, because we know that this identity will stay the same until the end of the computation. On the other hand, if we do Schrödinger picture simulation, then there are no fixed points. And this means that we need to continue our simulation from the beginning until the end of the circuit. We are never like lucky and we never know that we can like stop in advance. So like beyond that, there are also many differences between these three classes of noise. So for the dephasing class, we can use entropy accumulation bounds, and they will tell us that if you have a circuit with local noise at each layer, and the noise is depolarizing like, then after log n layer, the state will converge to the maximum mixed state, and then any expectation can be guessed to be 0 with high probability. But this doesn't work if the noise is dephasing or non-unital. Actually, if the noise is non-unital, so while for depolarizing noise you can only compute for logarithmic depth, if the noise is non-unital, it is actually possible to compute for an exponential depth without never injecting fresh ancillary qubits. And this can be done through a construction which is known as quantum refrigerator. And the intuition here is that noise is if we just take some qubit and we don't act on them, so we will put them in a sort of refrigerator. The noise will cool them down and push them down towards for example, the computational zero state. And this will provide us with fresh qubits. And once we have fresh qubits, that is like pure states, we can implement error correcting codes. So a consequence of this scheme is that there are worst case circuits with non-unital noise that are not classically simulable. And this is also one of the reasons why in this work, as well in previous works, people consider average case assumption to analyze non-unital noise. And there are already several works on the impact on non-unital noise in random quantum circuits. So in this previous work with Antonio and others, we showed that non-unital noise in random circuits can produce a noise-induced shallow depth. That is, if you have a very deep circuits, only the last logarithmic depth, only the last log n layers will bear some negligible influence to expectation values, and all the rest of the circuit can be neglected. This is because noise is effectively resetting qubits to 0, and then is erasing the information, but at the same time, by resetting them to 0, is like creating new pure states on which we can compute. Instead, the polarizing noise is setting the qubits to the maximum mixed state. On the one hand, in a similar way, this is erasing information, but it's also not providing new pure qubits on which we can compute. And another important qualitative gap, which actually predated the work on noise-induced shallow depth and actually was an important inspiration for us, is the effect of non-unital noise on random circuit sampling. So it was shown that random circuits with non-unital noise are not anti-concentrated. This means that their output probability is more peaked than the output probability of circuits without noise. So we lack this property of anti-concentration, and this has several implications.
Armando, before you move on, I just wanted to ask you a question about the first paper in that picture. So when you want to do a simulation in this setting, I assume for something like amplitude damping noise, you assume that the state is in the all zero state at the start of the green region, and then apply your circuit to that in the green region. Is that how you do a simulation?
Well, yeah. So actually, so you can insert any state at the beginning of the green region, and like for any state, you can approximate with a good precision the expectation values. So yeah, you can put whatever states is more convenient for you. Either, like I would say, if you are doing a classical simulation, I would put the maximum mixed state because it looks easier in the Pauli basis. Like if you are working with the Pauli basis, I would put the maximum mixed state.
But then, I mean, isn't everything just like the trace of your observable or whatever? Like, why do the simulation? Like, because if you put in the maximum mixed state, you basically, I guess because it's non-unital. So
yeah, exactly. Because now non-unital noise is so a channel is unital if and only if is adjoint is trace preserving. Then in the Heisenberg picture, the non-unital channel becomes unital, but it's not trace preserving anymore. And this means that when you apply the channel on the Pauli X, for example, or on the Pauli Z as in amplitude damping, you can get an identity. And this identity will overlap with the maximum mixed state. Will give non-zero overlap. So yeah.
Okay, cool.
And like eventually, if you do simulation in the Heisenberg picture for long enough, you will get so your operator will mainly consist of identity terms because all the non-identity terms will be suppressed. And this is why you can overlap with any state.
Okay, cool.
Yeah. So yeah, like one implication coming from the quantum refrigerator is that average case assumptions are necessary. In particular, so yeah, I also want to remark that it's important to have some assumption on the circuit itself. So in some previous work, people have considered worst case circuits on random states. And this for us would not be sufficient because you can, even if you start with a random state, you can like wait a few times and for example, if you are working, if you start with a random computational basis state and you apply amplitude damping for long enough, you will get the computational zero state. Then you really need to have some assumption on the circuit itself. Now we said that we don't have the anti-concentration property, and this means that the previous argument by Aronov and et al. On classically sampling from random noisy circuits doesn't work because their argument used anti-concentration, and this is still an open problem. We don't know. Maybe there is another argument that one can use to prove that even with non-unital noise, you can sample from noisy circuits, but so far it has not been answered. And regarding expectation value, since we have absence of barren plateau, we know that even for long circuits, we cannot just guess zero. but we need some proper simulation algorithm. Now, since the effective depth is logarithmic, we could use previous results for simulating log depth circuits. For example, like there was also a previous result of ours on Pauli propagation on noiseless circuits. The same construction would work more or less also with noise. But then this algorithm is not always efficient. So in general, if you want polynomially small precision, the runtime can be quasi-polynomial, and you can improve it to almost polynomial by adding some all-to-all interact, but sorry, by adding some geometric locality. But in general, the runtime will not be polynomial. Yeah, on the other hand, in this work, we do prove that there exists a polynomial-time algorithm for Pauli propagation equipped with pathway truncation under any sort of local noise under some average case assumption of the gates. So the algorithm consists in like computing all the Pauli-path and by truncating those with the larger path weight. There's a tab here in weight, which is basically the same algorithm that was also used in previous works on Pauli-path simulation. And so so our contribution is mostly proving that it works even for any kind of arbitrary noise. So we achieved this under a polynomially small error. We assume the noise to be incoherent. That is, we assume the noise channel to have also a non-unitary component. Sometimes people also consider unitary noise, which is like beyond the scope of our work. Our average case assumption can be told as like, so we assume that any layer is sampled independently from some ensembles that are invariant under single-qubit one designs, for example, single-qubit Pauli gates. And this is actually a weaker assumption than those considered in previous work. In other work, people considered ensembles invariant under single-qubit 2 designs or even under 2-qubit 2 designs. And there is no assumption at all on the geometric locality. So in a nutshell, previous works had a stronger form of randomness and also very specific noise models. And on the other hand, our results are for circuits with minimal randomness and arbitrary local noise. One weakness of our...
Can I just clarify? I think you might have already said this before, but yours is an average case result, is it?
Yeah. So yeah, we have a distribution over random circuits, and if we sample one circuit from distribution, we know that with a high probability, this circuit is simulable. Yeah. So one weakness of our setting is that we assume all the gates to be independent, or like all the layers to be sampled independently. So circuits with correlations, such as real-time evolutions, are beyond our theoretical results. So there is also like a small comparison with the other works on Pauli propagation. So yeah, maybe I will not dive too much into the comparison because there are various technicalities. But let me mention that there is also another work on simulation with non-unital noise that we posted on the same day on the archive that exploits a different strategy. Now, instead of truncating according to the path weight, we truncate according to the frequency. So the frequency is how many times the branch splits under unitary evolution. And whenever the noise is applied, if the noise is applied on edge Z, for example, if the noise is amplitude damping, we get a high branch and a Z branch. And in this work, we sample these two branches randomly. So we actually do a randomized version of a previous Pauli propagation algorithm, and we show that under amplitude damping noise, it works. So I also want to give a bit of more technical intuition behind our results. So, like first of all, let me comment a bit on the case of depolarizing noise, which was studied in previous work. It is useful to understand why, even for non-unital noise, this truncation works. So a single-qubit depolarizing channel can be told as a channel that with probability 1 minus p leave the state unchanged, and with probability p, it maps it to the maximum mixed state. And in the Pauli basis, this action can be represented as follows. We take an n-qubit Paulis. We apply the tensor product of n depolarizing channels. And what we get is the same p back with a prefactor, which is exponentially small in the Pauli weight. The Pauli weight is the number of non-identity terms in the Paulis. And before, I also mentioned, without defining, the path weight, which is just the sum of the weights of all the Paulis within a path. And the path is a sequence of Paulis. Yeah, maybe I should have put some definitions before, but I hope it is clear, or otherwise feel free to ask questions. And then, like, this suppression of the Paulis also leads to a global suppression of the operators in terms of the Frobenius norm. By Frobenius norm here, we only mean the L2 norm of the coefficients in the Pauli expansion. And these norms get suppressed as in this equation here. Then, like, some terms will be suppressed more, the high weight terms, and the low weight terms will be suppressed less. And this also means that if we only take the low weight terms, we can get an observable which is close to the original one in Frobenius norm. So why this is useful? It is useful because we know that if we discard if we take an operator and we truncate a portion with low Frobenius norm, then on average we are doing a low error in terms of expectation values. And yeah, this was like a technical results provided by Thomas Schuster in his paper of last year on classical simulation with depolarizing noise. So we take any ensemble of random states that satisfies this low average property, and a typical example are random computational basis states. And then we compare two observable, one truncated and one not truncated, and the average error will be small if the difference in Frobenius norm is also small. But then, crucially, this approach doesn't work with the non-unital noise. And the reason is that non-unital noise can actually increase the Frobenius norm. So this is an example in which we take some simple operators consisting in three Paulis, ZZ, IZ, and ZI. And then we apply amplitude damping noise. And one can actually check. Here, for simplicity, I put Q equal to 1, but it works also for other values of Q. Like, we can actually check that the Frobenius norm has increased. And yeah, so like trying to use the Frobenius norm to upper bound the error with non-unital noise will actually not be successful unless we employ some tricks. So this trick is a channel decomposition, which again was also part of this work of Schuster and others, but it was like in a very restricted setting. They considered only a very specific version of randomized spontaneous emission channels. So we can take any channel n and write it as the consecutive application of two linear maps. One maps will be the depolarizing channel, and the other maps will be some non-physical channel, which we call here n tilde p, which can be represented in this way in the Pauli basis. So this channel is still so it is still trace preserving, But then when applied on a non-identity, so the adjoint is still unital. But then when you apply this channel on a non-entity Pauli, we can actually increase the magnitude of this Pauli of a factor of 1 over 1 minus p. And we can see from this as this channel is non-physical because it can increase the 2 norm of a state, which is the purity that should instead not be. Yeah, so yeah, for many reasons, this channel is not something that can happen in reality, but it has very nice properties under average evolution, under random evolution. So if we take any, if we consider a one design, and then we sample a unitary, a tensor product unitary, such that each gate is sampled from a one design, and then we apply first this unitary on an operator, and then we apply these non-physical channels, we know that on average, the Frobenius norm does not increase. And this is very good news because before we had also some departing channel that is going to decrease the Frobenius norm. And then overall, this is telling us that any channel with this construction can decrease the Frobenius norm. Now, the important thing is how we set this this effective noise rate P. And this effective noise rate, in order for this to be true, should be set according to both the unitary D and the channel N. So the interplay of each noise channel and random unitary gives a different noise rate. But we show that in a broad range of cases, this effective noise rate will be less than 1. And in particular, it is always less than 1 if the unitary we consider is sampled from, for example, from a 2 designs. For non-unital noise, actually, a 1 design is already sufficient. Now, like exploiting this trick, we can actually also apply previous proof techniques that were developed for depolarizing noise. And we show that for exploitation values, the average simulation error is exponentially suppressed in the path weight k. Now k is some cutoff we set, and in order to compute the approximate observable, we do this simulation in the Heisenberg picture via Pauli propagation, and we discard all the branches that have a path larger than k, that have a path weight larger than k. And this also results that we can like test with our numerics, but I should say Manuel's numerics. So first of all, before even testing the simulation error, we check that indeed with non-unital noise there is no barren plateaus, and this effect is stronger and stronger as we increase the noise rate. And this simulation, as also other simulation this work, is something that has been done via Markov chain methods. And now the idea is that many second moments of random circuits and also random noisy circuits can be efficiently estimated by using a Monte Carlo methods that consist in sampling different Pauli paths. So this works for the variance, but it also works for the mean squared error. And this is very interesting because it allows us to have a very good estimate of the average error of our simulation without needing to also perform a brute force computation. Because typically for most simulation approach, if you want to get an estimate of the error, you need to like run your simulation and also run a brute force computation and compare them, but this can work only for a very small system size. And on the other hand, this Markov chain approach is efficient, is polynomial in system size. So this allows us to get very good estimate of the error, even on dozens or hundreds of qubits. So we can see that the actual error is indeed smaller than our theoretical guarantees. So Pauli propagation tends to perform better in practice than in theory. And this is because we we consider a very simple model in which we only look at single qubit randomness and single qubit noise, but in reality, there are also other effects, such as the entanglement, that are not part of our theoretical models. We are agnostic of the entanglement, but the entanglement can actually make the simulation error smaller. And so we also have other simulations which are beyond our theoretical results. As I said, our theoretical models requires the random gates to be IID or to be at least independent. And this is not the case in many physically motivated models of real-time quantum dynamics. But what we tested here is the robustness of our estimators. That is, we tried to simulate the same dynamics with the different truncation cutoff that you can see here. They range from 20 to 30. And we can see here that especially for small simulation time, the convergence in truncated path weight is very fast. And as the simulation time increases, and especially as the noise is lower, then our estimator is less robust, and it takes longer to converge and we need to increase the path weight more and more to get the convergence. Yeah, a very important thing is that there is an open source simulation library on Pauli propagation, and the main contributor are Manuel Rudolph, Yanting and Tyson Jones. And this library was used not only for this work, but also for a series of works on Pauli propagation and hopefully many works to come. And I invite you all to check this library. It's written in Julia, so I guess maybe more people have familiarity with Python. With Python. But yeah, like for some technical reason I'm not aware of, Julia was like the best language for this kind of classical simulation. And I think it's also pretty easy to learn because this library is also equipped with several tutorials. And yeah, so thanks a lot for inviting me, and let me know if you have any questions.
Thanks, Armando. I have a couple of questions.
Yeah.
Maybe first, I guess there's no anti-concentration in your setting, so does that rule out sampling? Can you guys do sampling as well as expectation estimation?
No. Yeah. So like our truncation rule was the same. It's the same truncation rule that Dori, Tarnov, and others have used for sampling. Then one would expect that it could work for sampling. And we didn't test it experimentally, so numerically. So this is something that one could do. But from the theory side,
but for sampling, they additionally used anti-concentration.
Yeah, indeed. Like there is this gap of anti-concentration which we don't know how to fill. So like theoretically, we don't know how to prove that this would work for sampling. Like there are also non-numerics on that maybe one can just test and see that it works surprisingly well. But yeah, I really don't know if this strategy, at least if this algorithm could work for sampling, or if we need other adjustment.
Okay. Cool. I had one more question about the numerics. Do you mind just going back? I don't think I had enough time to actually understand what the numerics was showing. No, not that one, the one after.
Which one?
No, the one you just passed. Yeah, this one. So no, not this one. The one where you show the expectation value as a function of time for the different truncation.
Okay. Yeah. So this last one.
Yeah, this one. Yep. So if I'm reading this right, the solid lines are the actual expectation value, And
yeah,
dotted lines
they are all expectation values, but they are computed with different classical algorithms. That is, with Pauli propagation equipped with different truncation cutoff. And for very short time, you can see only one line for the 3 noise rates. And this is because whatever path weight you use, you will get more or less the same result. This is not telling you that the result is correct, but it's a good hint that it could be correct, because by increasing path weight, the simulation is stable. But then
so
when
sorry,
you start,
what's telling you this? So if you increase path weight, so path weight 30 is, yeah, I guess, I mean, first of all, I'm confused by the fact that the expectation value is changing over time. So what is, yeah, but I don't know what the actual expectation value is. So you're saying,
yeah, we do not. Yeah.
okay. So
yeah.
what should I take as the proxy to be the correct answer? Like,
okay, yes. So this is like a simulation beyond our theoretical guarantees. And it's also on a very large system size. We have more than 100 qubits. And then like in this regime, is not accessible to perform also a brute force simulation. So yeah, but what we do here is we run the same simulation for different noise rates, different like different length of the time evolution and different path weight. And one would expect that the higher path weight is also more accurate. Again, this is just an heuristic, but it's something natural to assume. And what we see for short times is that whatever path weight you choose, you get more or less the same result. And this suggests that the estimator is converging very fast to the true value. Again, this is not super rigorous. But now, if you start increasing the simulation time, especially for lower noise rates, you see that very soon the estimators with higher and with lower path weights returns very different values. So this suggests that at least the simulation with lower path weight are incorrect. We don't know if those with higher path weight are correct. On the other hand, this effect is less prominent if we take higher noise. And taking all together, this suggests that the higher the noise, and the shorter the evolution time, the easier is to simulate, and that and so like the thing is that for a high noise or for short simulation time, any path weight from 20 to 30 gives more or less the same results. And increasing the path weight even more will not change the result. So this suggests that even path weight 20 is actually a good simulation, gives a good approximation for the simulation. But again, this is an heuristic. But this is to show that in principle, one could use this simulation approach even beyond our theoretical guarantees, with very strong assumption to prove theoretical results. But in practice, you can push this simulation further.
Mm-hmm. Can I just ask, you said that it suggests that for the higher noise, the effect is less prominent, but could it be that the effect is just happening later? Because I mean, this figure cuts off time equals 1. Have you looked at later figures and you actually see that it is less prominent as opposed to just being delayed?
No, but I would expect this to be the case, as you said. Like it will be delayed. And actually, even at time 0.8, even for high noise, we start seeing a discrepancy between 20 and 30. It's less prominent, not in the sense that it's cancelled. It's only delayed. Then I totally agree.
Okay, cool. Thank you for that.
Yeah, thank you.
All right, I guess we can give other people opportunity to ask questions. Actually, I just have a sort of basic question. So when you consider this kind of like path weight, I just want to have some idea as a sort of like not really knowing this kind of technical details, like how much truncation is actually meant by this kind of weights. So how much simplification is actually going on if you have like path weight of 20? Is there sort of like a, I guess it's hard to precisely say that.
Okay, yeah.
Like how much are you saving compared to sort of like exactly doing the thing? I don't know. I
Yeah,
can't
so
even
for
properly ask the question.
yeah, no, this is a very good question. So like the error is suppressed exponentially in the path weight, which means that in practice we need to set this path weight logarithmically if we want polynomially small error. And one can prove that even for logarithmic path weight, the simulation time is polynomial. Then like the runtime is going to yeah, I think you can like set this value at least yeah, logarithmically in system size. And actually like counting the number of paths for a fixed path weight is not something super easy. So yeah, it's not super complicated, but there are many like combinatorial arguments involved. Then I would say that the number of path weight that you can get is roughly exponential in path weight. But yeah,
I guess like in this case, the number I'm looking at is like, so there's like 121 qubits. That's sort of like the number where you're saying that it's logarithmic in that, right?
Yeah.
Or
yeah, so like the total number of branches will be polynomial. So we will choose the path weight like logarithmically in the number of qubits, and we expect that this lead to a runtime which is polynomial in the number of qubits. Like
okay.
Actually, so if we in some other works, especially in the noise-free work, we considered a different truncation rules in which we were truncating the Paulis according to their weight. So the rule was applied locally and not globally on the entire path. And yeah, okay, yes. So if you truncate according to the weight of individual Paulis, the simulation time will scale as n to the k, where k is the cutoff. But if you take the weight of the entire Pauli path, the simulation time will be like exponential in the path weight. So it will become independent of n. Like you have again the dependency because you set the so for example for a path weight of k equal log n, the simulation will be polynomial. On the other hand, if you truncate all the Paulis with weight log n, the simulation time will be n to the log n. So taking the weight of the entire path is like actually way more advantageous than taking only the weight of individual Paulis.
All right. Okay. Yes. Okay. Let me check if there's anyone else who wanted to ask questions. Or maybe Jakob used to have other questions.
No, I think I'm good.
Right. Yeah, I think okay, so maybe just one small thing. So because you mentioned this other work where you do this frequency.
Yeah.
yeah, this random frequency thing. So okay, I don't know. Is there like how does this kind of like compare with this kind of results here? Okay, maybe this is too early to ask, but maybe you can just briefly comment.
Okay, so we had a different motivation here. We are considering different kinds of circuits, which in a sense are more realistic kind of circuits, because we were taking Clifford circuits with the RZ rotations, which are used in many proposals for variational quantum algorithms. And we were assuming the noise to be not uniform, but gate-based. So the noise is applied only after the the Pauli rotations. So one difference here is that this other result is only established for amplitude damping noise and for other families of noise, but anyways, it's not fully general so here we have less assumption on the unitaries, but we have also a less general noise model. The setting is a bit different. And within this setting, actually, we saw that at least technically it didn't look possible to establish a simulation results by using pathway truncation. And this is why we came out with a different strategy, which now, so frequency truncation is something that we're already used for circuits with the depolarizing noise. But with the non-unital noise, you also get the noise to create new branches. And then whenever some branch is creating by the unitary itself, we use the old truncation rule designed for the depolarizing noise. And whenever the new branches are creating by the channel, we sample them randomly according to their weight. So when you have a Pauli Z and you apply amplitude damping noise, you get an identity branch with weight gamma and a Z branch with weight y minus gamma. So this two weight already gives you a probability from which you can sample. And so yeah, maybe so one important thing here is that when the noise creates two branches, their weight it typically sums up to 1. But when a unitary creates two branches, the sum of their weights is larger than 1, because so if you get a cosine and a sine branch, cosine squared plus sine squared is equal to 1, but the absolute value of cosine theta and sine theta is typically larger than 1. And this is why you cannot randomly sample from branches created by the unitary, but you need to make a choice and truncate one of them. And on the other hand, when the branches are created by the noise, so noise is in some sense more classical, because it creates some sort of probabilistic combination of two Paulis. So yeah, this was the intuition why with noise we can randomize the previous truncation rules. And so yeah, but this so far is only theoretical. For this other work, we also have less numerics, and maybe it would be interesting to numerically compare the two works. It's something that we have not done yet.
Yeah, okay, I see. Yeah.